Hello, my name is Mitch Goldberg. I'm a professor at chemical engineering and a distinguished research scientist for the NOAA CESART program. I retired from NOAA after nearly 35 years on May 31st, 2023, and the next day, June 1st, I joined CCNY to also be part of the CESART program. NOAA CESART provides stipends for students to conduct research in Earth system sciences and remote sensing technologies. Each student develops a research project, works with a NOAA mentor and faculty mentor, including a 12-week internship at a NOAA facility with the goal of working at NOAA after graduation. And one of my responsibilities is to help students develop their research plan and their mentorship and their internship as well. Let me tell you more about my career, about how satellite Earth observing systems or satellites support chemical engineering, with examples of different satellite systems, and then some of the research I'm starting up at CCNY. Remember, this is my very first year, and so I'm just starting out, but you'll see that I'm already starting to conduct a lot of interesting research. I'm not going to read everything on this timeline, but it will give you a sense of my experience. So in the 1980s, actually 1979, I was a meteorology student at Rutgers, actually Cook College. I had, from 77 through 81, I had an internship at NOAA at the Satellite Office of Research and Applications in 79, also 80, 81. I loved it. I loved satellite remote sensing. I went to University of Maryland, got my master's degree, and then I became a contractor and then a federal employee in 1990. And my focus area, my research area, was and still, for the most part, is atmospheric soundings from different satellite sensors, mostly in the microwave and infrared, but I've been expanding in different part of the spectrum, which I'll show examples later. I developed the first physical algorithm used operationally at NOAA. In the 1990s, NASA flew for the very first time, or was getting ready to fly because it didn't fly until 2002, the very first hyperspectral infrared soundings. And I was selected to serve on the air science team. I also developed the very first satellite climate data record from NOAA microwave sounders. I got involved in radiance data assimilation, which is the use of satellite data directly in weather forecast models. I became more involved in international working groups, particularly in atmospheric soundings. In the 2000s, I decided to take a leap and went into research management, where I became a division chief for the Satellite Meteorology and Climate Division. It was a very, very large division, 120 federal employees and contractors and university employees too through cooperative institutes. While I was there, I developed a new science program for GOES-R, which is a geostationary satellite system. I then became more involved in international programs. I became involved in the NOAA Climate Board. I supported the development of, I know these are acronyms in there, the National Academies of Sciences Climate Data Record NOAA Report and Recommendations, which we then implemented. I first then became associated with CCNY through CREST. So CREST was the former name of CESART from 2001 to 2016. And so I was on the advisory board. And then I actually went back to school. I actually went back to school in 2001, where I then eventually earned a PhD in 2009, because it takes time while running a division and taking, conducting research. Luckily, most of my courses I already had when I went for my master's degree. So that took a while. That was a lot of work in the early 2000s. Then in 2010, I became the chief scientist for NOAA's Polar Orbiting Satellite Program. I'll explain what a polar orbiting satellite is. It's called JPSS, Joint Polar Satellite System. I developed the JPS Proving Ground, which is focused on innovative use of satellite data, plus including applications. I then became the chair of the CCNY CREST Science Advisory Board. I became the co-chair of this international sounder working group, which I got involved in the 1990s, and other things. I actually led this interesting project generating flood maps from satellite data. It became the first operational flood mapping project or flood mapping product from NESDIS, which, by the way, is the name for the NOAA satellite program. In 2020, May 2020, so not too long ago, I became the chief scientist for all of NESDIS. I developed an enterprise program for Proving Ground. I then became involved in a lot of executive decisions and coordination amongst all different parts of NOAA. So during this distinct period of time, I became very involved in other parts of NOAA. NOAA has Weather Service, NOAA has the National Marine Fisheries Service, the Ocean Service, the Office of Oceanic and Atmospheric Research. So I got to know practically all the leaders in those what we call line offices. And then this opportunity came up to be the Distinguished Research Scientist, which is a key position for CESCERT. I applied and I started on June 1st, 2023. So you may be asking the question, Earth remote sensing, what does that have to do with chemical engineering? Well, quite a bit. Earth remote sensing informs chemical engineering. We have environmental monitoring, where Earth observations provides invaluable insights into air and water quality, soil composition, vegetation health, for example. That's really important for assessing the environmental footprint of industrial operations. By continuing monitoring, for example, air quality and water quality, chemical engineers can figure out how to mitigate or reduce the impacts of pollution. So that's really, really important. For disaster response and management, chemical engineers are pivotal in disaster response and management, particularly in handling hazardous materials, mitigating environmental disasters. So Earth observing satellites can provide real-time surveillance of wildfires, for example, floods, oil spills, and chemical leaks. So we do have satellites from space that can actually look at leaks, like, for example, methane leaks. Can look at harmful nutrients, runoffs, sediments into local water supplies. And climate change mitigation, combating climate change demands a collaborative effort with chemical engineers at the forefront of developing solutions, carbon capture technologies, greenhouse gas reduction strategies, and Earth observing satellites provide data for modeling, for climate modeling, for monitoring temperature and changes and precipitation and greenhouse gas levels such as carbon dioxide and methane, and this information is critical. So here's a very, very quick overview of remote sensing. The sun emits energy, the Earth receives energy. The energy is also referred to as electromagnetic radiation. The Earth's atmosphere will interact with that energy in different ways. It absorbs the incoming energy and releases it at different wavelengths. It reflects the incoming energy from the surface and from clouds. It will backscatter the energy from particulates. Here we're showing the electromagnetic spectrum from radio waves, microwaves, infrared, and ultraviolet. And these are the different instruments and what we call imagers and sounders that we have. So we have UV, vis, near-infrared imagers. We have vis, IR imagers. We have infrared sounders, microwave imagers, altimetry, scatterometers, radio occultation. And from these instruments, we can derive a whole range of different products. atmospheric composition, air quality products, for example, aerosol concentration or aerosol optical depth, atmospheric temperature and water vapor, clouds, lightning, precipitation, radiation budget, tropical cyclone information, volcanic ash, winds, ice, lake and sea ice, snow and glaciers, fires, floods, surface moisture, surface temperature, vegetation, biogeochemistry and biology, and surface height, topography and bathymetry, water pollution, water temperature, a range of space weather information on the heliosphere, ionosphere, the solar disk, the magnetosphere. So a lot of information, and at CCNY you will also learn about remote sensing technology and deriving information from outgoing radiation. This slide is from Dr. Dylan Millett from University of Minnesota. It basically shows a wide range of atmospheric compounds that can be derived from satellite data from instruments measuring outgoing radiation in the UV visible, in the near infrared, and the thermal IR. We're going to have a lot of these capabilities from our new geostationary GeoXO instruments and from other sensors from our international partners as well as from NASA. So it's an application and that we will be working on at CCNY. So the problem is that, as you know, most of you know that CO2 has been increasing quite a bit since the industrial age. It's been increasing steadily, and as a result, temperature also has been increasing steadily. And the problem is that we have to reduce emissions. And so this is an example of goals that are being set. Can we turn this around and start reducing CO2 emissions? And if we don't, and if it's business as usual, you can see that the expected temperatures are going to increase quite a bit. We're trying to curb the temperature increase to this level, and to do that, we really have to make strides to reduce emissions. It's very, very difficult to do. And so we have to, I'll show you an example of what New York is doing with respect to reducing greenhouse gas emissions. Because of CO2 rise and because temperatures increasing, it has been causing havoc to our environment. This is from NOAA, from our National Center for Environmental Information. It shows the number of disasters, number of billion-dollar disasters since 1980 as a function of time, all the way from 1980 to 2023. And you can see there's a steady increase in the number of billion-dollar disasters. So it's going to keep on increasing. And what we have to do is not only monitor, but look at trends and look at how we can mitigate and adapt to these climate impacts. And that's, again, a job for engineering. So it's very important that the data itself provides you with the evidence, the information needed to come up with the solutions that are needed. Here's a chart between 2021 and 2023 that shows where these billion-dollar disasters were. And so you see in 2021, there were a lot of fires in the western, in the western regions. In 2023, it was different. We don't even see one fire. Unfortunately, there was a big fire that resulted in a lot of lives being lost in Hawaii and Maui, which I'm sure you heard about. But in 2023, it was all about atmospheric rivers and flooding. So it's very important to be able to predict these events and in order to come up with, again, solutions to mitigate, to adapt. Now, I promised that I would talk about what we're doing in New York. So here's an engineering solution. So CCNY is very much involved in New York City's Green New Deal. And there's something called Local Law 97. So New York City used all the data that we've collected or observed from space and other other ways from ground-based measurements, and basically said yes, CO2 is increasing, and yes, temperature is also increasing, and severe weather is increasing, and we have to do our part. So they decided they're going to become carbon neutral by 2050. They noted that 2/3 of all greenhouse gas emissions are from buildings. So they're going to try to reduce by 2030 to reduce greenhouse gas emissions by 40%, which is remarkable, which is very progressive, and by net zero by 2050. Now, how do you do that? Well, you build more efficient um, um, energy systems, heating systems, cooling systems, solar power, things like that. And CCNY engineering is doing a lot of this development. So we're playing a part, but remember, it's the data, the information that informs the decisions, because there's something called a return on investment, and what if we didn't make any of these changes? You're going to have more buildings, coastal flooding, all these impacts. That's really going to have large negative economic consequences. In addition to our lives being disrupted. So my areas of expertise is in Earth observing satellites, atmospheric radio transfer, all different applications from satellite observations for both weather and climate, atmospheric temperature, water vapor soundings, and greenhouse gas emissions from satellites, wildfire, smoke, aerosol transports and impacts on air quality, and flood detection, both local, current, and also climate scale, understanding trends in flooding. Remember, if we notice that, for example, that a particular area, instead of getting floods every 10, 20, 30 years, but now flooding is occurring, large floods occurring annually, then that information is used to make decisions on changing building codes in order and seawalls in order to mitigate, adapt to climate change. So again, environmental information is important. And so I worked at NESIS for many, many years. And at NESIS, we operated satellites, developed science algorithms, and also kept on planning for next generation of satellites. So at NOAA, we operate two types of satellites, polar orbiting satellites. So this is at a lower altitude, 540 miles roughly. And as it's orbiting from South Pole to North Pole, the Earth is spinning underneath it, and so we see the entire planet. The geostationary is at a much higher altitude, 22,300 miles, and it's moving at the same speed as the Earth is moving, so it looks like it's always overhead, and that's what we call our center of the sky. So here's an example, a recent example of goes west and east. These are NOAA satellites, and you can actually see the atmospheric river events as causing quite a bit of flooding in California. And so here, this is how we monitor our part of the world. West and east, we require 2 satellites, and other countries around the world also have their own geostationary satellites. Now, most of our NOAA satellites have been focusing on monitoring weather, but we are now expanding to monitor air pollution and ocean biogeochemistry. This is an example of the new NASA TEMPO geostationary instrument, which monitors air pollutants hourly, and there will be a NOAA operational follow-on. And from polar orbit, we have, or from low orbit, I should say, we actually have 2 orbits. One is sun-sync polar orbit, and then we can actually have a low inclination angle that basically sees just the tropical areas, and that improves the diurnal refresh. So we get to see more times during the day. A single polar orbiting satellite will see the same area about twice per day, especially near the equator. But again, this is important for observing the entire planet and for climate studies. So we use both geostationary and polar orbiting satellites. So at NOAA, I'm talking more about NOAA because I retired from NOAA, but we operate 16, I think now 17 satellites. This is an old slide. But when you look, bring in together NASA and international satellites, it's tremendous. We have so many satellites up there, and so the challenge is to use all this data to make sure all the data is open and free and accessible using cloud technology, bring all the data, intercalibrating the data, which means comparing one satellite with another satellite to understand the differences, to account for any differences so we can use them in applications. And so we at NESDIS, at NOAA, we take all these observations from different sources, our own satellites and partner satellites, from even commercial data, ground-based data. We turn them into data products, information products, and services, and they basically serve mission service areas like forecasting the weather, forecasting coastal water quality, ecosystem monitoring, assessing climate change. So there's a lot of applications listed here. And NOAA, there's this vision that it all has to do with climate change, and we're focusing on making sure that NOAA, working with other agencies like NASA and the Department of Agriculture and others, to make sure that the nation has the information needed in order to reduce the impacts of climate change. We call this a climate-ready nation. So what am I doing? So at CCNY, I've started new initiatives to support different areas, supporting actually NESDIS and NASA. I have, I think, 4 projects. One is that we're actually taking at CCNY, we have incredible ground-based observations that we're going to use to validate satellite products. So remember I showed you earlier that tempo products of nitrogen dioxide. We're going to validate that with our in situ data, our ground-based data, as well as other products like aerosols and ozone and other atmospheric composition products. And this is an example of all these type of measurements that we do have at CCNY, so quite a bit. And we're part of a larger network across the U.S. And what we're planning to do is we're taking an existing capability at NESDIS, at the satellite program. This is Aerosol Watch, which basically shows, this is a satellite image of very thick aerosols. This is caused by the Canadian wildfires. This was June 7th. If you were at New York during that week, it was so horrible. It was hard to see. Your eyes would burn, and you could smell that smoke. It gets in your lungs. It's very, very dangerous. So these type of products are important for helping mitigate health issues, air quality health issues. Noted here on these dots is what they call particulate matter 2.5 measurements from ground-based sites that has existed quite a bit. But everything gives you like a 2-dimensional. It gives you a 3-dimension in terms of time, but we're basically looking at a 2-dimensional XY information on, in this case, aerosol optical depth. What we want to do is take our data and be able to add functionality to it. And we have all these type of measurements. And we're going to compare them where we can click on these and look at, this is a ceilometer that looks at backscatter, and it's basically looking at aerosols. So it's looking at the smoke and the thickness and the aerosols as a function of height. So now you have this vertical dimension. And then you can use AI machine learning and bring both of these together and actually construct a vertical view of what, of the atmosphere with respect to with altitude. Another project we'll be getting support from NCI, which is from NOAA, National Center for Environmental Information. We're creating something called CHARM, the Climate Hub for Analytical Research and Monitoring. What we're going to do is fuse NOAA as well as NASA and other information, environmental information, with socioeconomic data. So this is how we're going to make big data easily accessible. We're going to be able to look at climate vulnerability scores to identify underserved communities that are under distress with respect to environmental conditions. And like I said, we're going to use AI, machine learning. And here is an example of the flood maps that I talked about earlier that I didn't really show, I just talked about it. But this is a flood map from satellite data along the Mississippi. And this is from early 2019. And then we can combine census data and see where the floods are impacting basically the different type of homes. In this case, single-family homes, detached, attached, mobile homes. We can actually click on economic, income type of information to see where areas where, for example, if you're going to worry about the impacts of flooding on a local population, you're going to say, I'm going to worry about the mobile homes first, where usually that's where vulnerable communities live. And so this information, the flood mapping combined with socioeconomic data, will be very, very powerful. Another research project I'm leading is using the new NASA CubeSat microwave sounders to monitor atmospheric rivers and water vapor. Because it's at a low inclination angle, the constellation of these CubeSats can observe this entire region over the entire diurnal cycle. So this region is about plus or minus 40, 45 degrees latitude. Now the top graphic is the original data, and the lower graphic is after a limb adjustment is applied. Because these are cross-track scanners, they'll have this limb effect because the optical path length is larger as the satellite or instrument scans away from nadir. So we have to make this adjustment. So clearly you can see after the adjustment, now the data can be used. This is basically a channel that is sensitive to upper tropospheric water vapor. And the colors that are red are where there's very high amounts of water vapor. Where it's blue, the water vapor is much lower. Now, even with this adjustment, each satellite in the constellation still has its own instrument behavior, which must be accounted for if you're going to use them in applications. The lifespan of these instruments are relatively short, a couple of years, and the orbit decays over time, which means that they need to be calibrated against benchmark measurements, instruments like ATMS, which has a stable orbit with a design life of more than 5 years. And the first ATMS is going on its 12th year. So these NOAA microwave sounders are quite stable and can be used for anchoring the small sat constellations, and we'll be studying how best to do that. Some of the research I did, this is actually did for my PhD dissertation. I used hyperspectral infrared radiances. This is from the AIRS instrument, which I was part of the science team, and we're looking at the hyperspectral infrared radiances are very, very accurate because the spectral resolution and spectral response functions are well known. It has an accuracy of less than 1/10 of a degree. So you can take different weather and climate models, simulate what the instrument would look like, compare the simulation with the observed, and start taking differences. And so, for example, if there was a change, if two models, for example, had differences in moisture, water vapor, about 15%, I should see a difference of one degree, a big difference. that 1 degree difference is much larger than zero point 0.1. So I should be sensitive. I should be able to figure out which model is more accurate. And so that's part of my research. So let me do some concluding remarks. So Earth remote sensing is very applicable to chemical engineering, climate mitigation, and adaptation solutions. My satellite remote sensing projects are not limited to the ones I am currently leading at CCNY. Through my collaboration with NOAA and NASA, new research projects can be established. Working with NOAA and NASA mentors, that would be very exciting, with my research group at CCNY. And again, the NOAA assessor funds master's and PhD students, so that also is a different opportunity that one could try to look at. And again, the activity is focused on working with NOAA scientists and CCNY faculty. And this is a flyer that talks about that program. And so if you want to learn more about NESDIS and NASA, about satellites themselves, you can go to these websites. It's very informative, and you'll be able to understand how satellites can actually support chemical engineering solutions. Thank you.